Welcome back, students. So in the last lecture, I told you how the moving coil galvanometer works and what are the different aspects that we have to take it into the account as we are going to calculate the voltage and the current sensitivity. Here, I am going to discuss a special case, not a special case, a technical aspect, because in the previous lecture I mentioned that the galvanometer is a very sensitive instrument, that it will not be able to even measure the current of 1 or 2 amperes, because it is only made to measure the currents of micro or milliamperes. So in order to overcome that constraint, here I am going to make some changes with the instrument so that that particular galvanometer will be able to measure even a huge amount of current. So what am I going to do? I am going to convert the galvanometer to ammeter to measure the huge amount of current, and simultaneously in the very next thing I will be converting it to voltmeter to measure huge amount of voltage. So first let me directly jump in. Conversion of galvanometer to ammeter. How do you think you are going to convert it like this? The purpose I have already said, the galvanometer being very sensitive, so I cannot measure huge amount of current using that. So I am trying it to convert it to a pure ammeter which is capable of measuring any amount of current if the necessary changes were made with the circuit. Okay, so now what exactly am I supposed to do to convert it to an ammeter? First thing is, you are supposed to connect a low resistance in parallel with your galvanometer. I repeat, you are supposed to connect a low resistance in parallel with your galvanometer. See, this is your galvanometer resistance G, and if I try to connect a very small amount of resistance in parallel with this, this will be able to measure a huge amount of current, which means I is the incoming current. And Ig is the current that is going through the galvanometer. Then this current will be I minus Ig. This resistance is called the shunt resistance S. Okay, you might wonder what is the physics behind this. You see, Ig is called the full scale deflection of the galvanometer, which means you are taking a galvanometer which is capable of measuring like 10 milliamperes or 10 microamperes like that, and you connect a very small resistance in the sense whose resistivity is very low, okay, which is almost a good conductor. I am connecting it in parallel with the galvanometer resistance. So the incoming current is going to go through your shunt resistance instead of galvanometer, because the current has a quality to find the easiest path. So most of the current will actually go through your shunt resistance instead of going through your galvanometer. So your galvanometer is safe to measure. Just for example, I am going to give you an instant. Listen. My galvanometer is capable of just measuring 10 milliampere of current, let's say. That is the maximum amount of current that my galvanometer is capable of measuring. But I am going to use that galvanometer to measure 1 ampere. So this incoming current will be 1 ampere, but this Ig, the current that is going through the galvanometer will be just 10 milliampere, and rest of the 990 milliampere will be going through your shunt, which is I minus Ig. I will be setting my resistance in such a way that only 10 milliampere goes to it, and rest of the 990 milliampere only goes through my shunt. So which adds up to 1 ampere. Which adds up to 1 ampere. You might think, sir, how to exactly engineer this? How do you say only 990 is supposed to go over there and only 10 is supposed to go in here? Because I'll be using a suitable resistance in parallel so that I can calculate exactly how much amount of current that is going to go through this. So what I will understand, whenever my galvanometer is going to show a full scale deflection, okay, whenever it is going to show a full scale deflection, I will understand that the incoming current is just 10 milliamperes. All the rest of the current would have gone through the shunt, which is 990 milliamperes. If 0.5 amperes comes in, 5 ampere will be the deflection shown in your galvanometer, and 445 milliampere would have gone through your shunt. Okay, so just by seeing the deflection made in the galvanometer, I can make a guess how much amount of incoming current is possible. Okay, how to do that? See, these two resistance, this is a galvanometer resistance and this is a shunt resistance. Both the resistance are in parallel. So, the potential drop on those resistance will be the same. See, Ig into G is the potential drop on this. That will be equal to I minus Ig of S. That will be I minus Ig of S, where S is equal to Ig into G by I minus of Ig. Ig into G divided by I minus of Ig. This is the amount of shunt. This will be the amount of shunt that should be implemented to get the deflection. So, you have to substitute your I, the amount of current that you are going to measure. Ig is the full scale deflection of the galvanometer, which is a fixed one, and G again is the galvanometer resistance, which is also fixed. So, by putting all those quantities inside this, you get to know how much amount of shunt that you are supposed to connect in parallel to make your galvanometer to ammeter, which is capable of measuring any desired current you want. This is a very important technique that is implemented. And now I am going to use the same exact thing to convert the galvanometer to the voltmeter. So, what do you think is your voltmeter? Voltmeter is an instrument that is capable of measuring the potential drop. So, this is your galvanometer, and if Ig is the current going through the galvanometer, let's assume. So, if I ask you to calculate the potential drop, how will you calculate? Sir, V is equal to Ig into G is the potential drop on the calculator, on the galvanometer, sorry, where Ig will be a very, very, very small value. Because what did I say? Galvanometer is capable of measuring something in terms of microamps. So, Ig will be of 10 power minus 3 and G will be of 5 to 10 ohms. So, together if you put, you will just get 0.005 or 0.00 something. So, that is the amount of potential drop that your galvanometer is capable of calculating. But now you are going to try and make your galvanometer so effective that it is capable of measuring even the high potential drops. So, what are you supposed to do then? You are supposed to connect a very high resistance in series with it. So what exactly happens then? You are going to connect a high resistance in series with it. V is equal to Ig into G plus R. You are going to connect a very high resistance in series with it, so that both the resistance get algebraically added. Now you see what is going to happen. That R will be in terms of 1000 ohms. G is something like 5 ohms, and if you multiply it with your Ig, the current, the minimal current, you will get a considerable amount of voltage, like 1 volt or 2 volt or 3 volt, so that your galvanometer gets converted to a device which is now capable of even measuring the huge amount of voltages. Okay, so the question in here will go like this. What is the amount of resistance that we are supposed to connect in series with the galvanometer in order to convert the galvanometer to measure the huge amount of voltage? So what you will do? You have to separate your R. See, first V minus of Ig into G is equal to Ig into R. I have multiplied my Ig into the bracket and I have taken Ig into G term to the left, and it is like this. V by Ig minus G is equal to R. This is the expression that you will be using to calculate the amount of R to measure which amount of desired voltage that you want to measure. So this is a very simple and interesting and an important topic, the conversion of galvanometer to voltmeter, because there are plenty of tricky questions that have been already asked in many competitive exams from these two topics. So I hope you people are so aware of whatever I have taught you today. In the next session, I will be numerically showing you how to apply these concepts into that. I will be solving 3 numerical problems on that. So I hope you will be attending that session too. We will meet there again. Thank you.